Can you hear me? Is that all good? Cool. So, not great with mics, just need to attach it somewhere. But, thanks to everyone for being really patient. I know it's really hard to sit in a room watching people talk about their nerdy stuff all day. It's very tiring, especially on Zoom, like when we did it last year. But I'm Kyle, and I'm going to talk you through Q3 Express, which is an assumption-free model of expressive human performance modelling, basically. And you're probably thinking, what is expressive rendering? And it is where we take performance data from humans, and we take input MIDI, which is a non-expressive type of data, and we teach an algorithm how to play like a human in hopes of increasing the expressive quality of music that's generative or not generative. Like, you could run a MIDI of one of your favourite songs for it, because MIDI is non-expressive. So, what does Q3 mean? And Q3 relates to the idea that if we look at a score, this is probably gobbledygook to most people. Generally, you just have the notes on the stave, and you've got a little symbol there for the key, and that's the time signature. Terrible at pointing, I am dyspraxic, so I apologise. Yeah, so basically on a stave, all you're really finding out is the pitch of a note when you should play it, because you'll be counting the pulse of the bar based on the time signature. So you have like a start time for a note and how long it should last. However, a lot of the more recent models, that, like especially using deep learning architectures currently, they use a wealth of score features, which is like the small left there tells you to play at a certain level of loudness until there is a new one. The symbols above notes tell you to accent certain specific notes, like that's hitting on the downbeat. You've got slurs that tell you you're not actually playing the second note, you're just holding it. So, score cues are instructions, essentially, that humans use to understand how to better represent the composer's intent. And obviously, for a very small fraction of a page, they give you a lot of data. So it is very useful for modelling. But we're games researchers, and if we were doing games, why would you have that in your game engine? You probably wouldn't, because people aren't playing it. And it's just more to encode. So I decided it would be a good idea to build a model where we're purposely giving it limited features that you would find in a game. Now, before you all glaze over and get bored, I do have some audio demos, but just to show you the visual representation first. The axes here are pitch for these, they're the individual notes over time. And on the bottom part, it's dynamics is the volume of how a note is played. And you can see here, this is like level. So this first one is non-expressive MIDI data. And this piece you'll hear in a moment was the input data that was used for the one on the other side, which has been rendered. But you can see the small white lines are a metrical grid. So all of the notes are falling exactly on a grid, which is something you would only expect from a robot or like a computer playing a piece of music. The ends of the notes also fall on the grid because the length of the note is set, and you can see that there's no variation in the loudness. So I'll show you how this sounds before I show you how things have changed on the other side. Just to let you know, that is actually put through in a virtual instrument, so it does sound better than MIDI. MIDI would just be an almost synthetic sound, but, you know, MIDI is hard to listen to even for people who are bothered about this sort of stuff. So, on the other side, this has been run through some transformers, but we'll get onto that soon. You can see, though, that the notes in particular don't land on the grid, and the end of the notes sometimes overlap with the start of the next note. They don't specifically land on the grid either. But also, the dynamics, the variation in the dynamics is a lot more apparent, like across the same notes. And it sounds like this. This is the rendered version without cues. exactly the same loudness and on beat. I also forgot to mention that when we see things like multiple notes on one place, tempo is the idea that a performer slows and speeds up basically throughout performance. So there is a tempo model that is doing notes where they all land on the same bar, but then they also have individual models for separate timings because you wouldn't press all the keys at exactly the same time. So this is important because it obviously is a successful expressive rendering, and a lot of the criticism that music that is generated gets is it gets called muzak because it's very non-expressive. So personally, I think that this is a key component in the potential revolution for using procedural music generation inside of games, because people aren't going to want to listen to it in the game until it sounds reasonably good, /human, or expressive. For a little bit of context, listener fatigue, it goes as far back as Berlin in 1976, and it's the result, it's a phenomenon in which repeated exposure to audio stimuli basically brings the enjoyment down, but it also eventually really, really annoys people. And I'm pretty sure everyone here who plays games has probably played a level and heard the same piece of music for 2 hours and been like, please just stop. But then the answer to that in a lot of modern games is after 20 minutes we're just going to fade it out, you could just be in silence, and it's like, oh yeah, this is great, left all on your lonesome to think. But it's not really a great way to handle those problems, it's just the only way in a lot of cases. So, because of spatial constraints as well, with audio for games, there isn't really the scope for having limitless audio, like I just said, for the 2 hours for completing a level. But to further contextualise it, in most games we're using pre-recorded human performances or mock-ups where it's virtual instruments. So you could have, you know, like a minute of waveforms. However, with a strong expressive rendering solution, we could solve listener fatigue and create a space for new creative possibilities in game audio to benefit of the composers, players and designers. And just to further contextualise that, symbolic note information, MIDI, it is sort of retro, non-expressive. If you think of Final Fantasy 7, 8 and 9, their soundtracks were MIDI, but they had extra post-processing. So that's kind of the quality you get with MIDI. However, 1 minute of audio waveforms is 10 megabytes or 10,000 kilobytes. 1 minute of multi-instrumental MIDI is 20 kilobytes. So if you have, for the space of 2 waveforms, you could have 500 MIDI pieces and an entire virtual instrument that is like every key on a piano at different note durations. So you could have 500 performances of different pieces for the same, and what's that, 20 megabytes? As game developers don't really give us in the audio side a lot of data anyway, so it is one solution. Now, for background, research has been conducted into how performers make decisions and how they think about music. Specifically how it relates to expression or how we interpret a score in order to colour the performance. But it's commonly suggested that tempo adjustments, which is the pulse that moves with how people play a piece, is very different for every performer, and that subtle dynamic changes, so loudness variation, is the toolkit of expressive delivery. And if we go to like the early rules-based models and linear regression approaches, you know, they are fairly successful. But when we go with the to more recent times, the continued development of deep learning architectures, it's seen continued dramatic improvement. And this is where, in the early models, they would use the reduced input features. They weren't considering score features a lot of the time. They just had rules like, if there are 3 notes and there's a contour, the middle one's the highest, make that a little bit louder. But just to show this, in one listening study recently, or a couple of them even, 2 deep learning architectures, one being a graph neural network and one being a hierarchical recurrent neural network, have both shown to massively outperform linear regression models, but they still rate lower than humans, in these excerpts at least. So, we decided to try and apply a transformer architecture, and the reason for this is, for people who don't do AI, a transformer, as compared to a normal feed-forward neural network, is capable of processing in parallel. It can do forwards and backwards at the same time, It's also, because of the attention mechanism, it's capable of looking at longer and longer sequences of notes. And a lot of computer scientists don't really consider music as a musician would. Like, it's not just about the riff, it's not just about the section of music, it's not just about the entire piece. It's sometimes about the opus. So the transformer architecture is particularly good at dealing with that and other temporal sort of features. So we used 4 of them. I started with just the input. I took MIDI and decided, how do we make this even smaller? How do we get more bang for our buck? So I stripped out the pitch, being like, is it a C, a D, E, F, so on. When does the note start, and how long does it last? And that's all we need for this model, instead of taking all the score features encoded into a full MIDI. And put that into a velocity model, which is predicting how hard each note should be played. All it needs is those 3 bits of information for every note in a piece. And that gives us a velocity prediction, obviously. But then if we combine that with the other 3 points of data, we can use 3 separate models. One to look at the start of a note and to predict adjustments to this, either forwards or backwards. We can do the same for the end of the note, which is the duration. And then we can finally model tempo. And we do that by using those the 4 points of information here. We go through the entire piece, and instead of looking at a note by note level, we look at beat by beat. And we start to look at the mean, the min and max number of notes per beat, and start considering how a person would be playing this. And then that finally gives us an adjustment prediction for the tempo. And then we sort of multiply these together in this way, and that gives us a very small, very slight adjustment to moving a note forwards or backwards and shortening the length in it, and we've got a velocity prediction. And that gives us just 4 points of data for each note, so all you're really getting is like a 2D array. So again, it's a very, very small data footprint. And when it comes to evaluating, we used it within participants' design. We had a baseline MIDI, like you heard. Everything was processed through the exact same piano sounds, for fairness. We had ours, CFE. VirtuosoNet is a model that uses all of the score features. It's probably the standard at the top of the field at the moment, unless the paper's come out yesterday. And then an actual human performance taken from the training data, but I'll discuss the training data soon. Actually, I'll discuss it now, it's probably worthwhile. There were 250,000 notes taken from the aligned scores and performances dataset, and we used a split of 80-10-10 for test, train, validate. And that's probably just nonsense to a lot of people. But essentially, there was a lot of note data there, and we could have got even more. But for each note, we'd synchronise multiple performances of the same score. And it's not just taking one person's performance style, it's making like a general model of performance across, I think there's 27 professional pianists who were in the data set. We did use 9 pieces. They come from Bach, Haydn, Schubert, and there was also Chopin. 19 people participated, more than that did, but oh god, that's very soon. Okay, as a lot of people will find, doing stuff over the internet because of COVID, it affects data collection. And all of these people, though, were music undergraduate or higher, so they had specific knowledge. They knew what to look for, because we were asking them to rate on metrics. So use of volume, use of tempo, use of timing, and overall expressivity, which is just cover for all the 3. So the next slide, I'm going to call this the 4 metrics. And we also evaluated it with a base factor analysis, which is a non-frequentist and non-parametric test. So here you can see the overall ratings for expression. There is a huge divide between human and ours. However, there is reason for this I'll get to. But you can see the score-informed model actually performed on par in a lot of ways, and we still performed much better than the baseline MIDI, as you would have heard at the start. And it's useful to contextualise, obviously, VirtuosoNet only performed as well as a human in these 30-second episodes. However, the divide here between the models could be because we're not modelling pedal use on the piano. CFE does, and humans use pedals. And this actually accesses a qualitatively better sample in virtual instruments, which we haven't considered, and that's where the model's being improved currently. As you can see, in dynamics, we rated much better than MIDI, and they've got loss ratings for people who care. But there is an argument for how important loss actually is compared to what you're hearing. So, in conclusion, although the model doesn't match human performance, it is a drastic improvement on MIDI, and it also could be the keystone in improving procedural music going forwards. It also, there is a potential concern here for discussing the performance of a neural network in a game. However, a few weeks of training to me, is a bit different to how long it takes to infer. Because of the small amount of data, it's very fast. Although the consideration for audio is very different to frame rate for games. You've got to worry about 60 frames a second. We have to worry about 44 1,000 samples a second. It's a very different margin. Milliseconds to us can be a problem. I just want to say thanks for listening. My supervisor is Tom, and I had a collaborator called Alex who helped with model design. Here are my references.